Okay, so in this video, we'll be continuing with what we started off in the previous video, and that was formation of salts. So we started off with defining what exactly a salt is, and we said that salt is a chemical compound formed by replacing one or more hydrogen ions of an acid with any other cation. Then I told you that it's not necessary that all hydrogens of an acid are ionizable hydrogens, and I gave you the example of ethanoic acid. It has 4 hydrogen ions, but it's only the hydrogen in this carboxylic group, COOH group. This COOH group is called the carboxylic group. In this carboxyl group, only this hydrogen is the ionizable hydrogen. The other hydrogens are non-ionizable hydrogens. Then I told you that there can be more than one ionizable hydrogen as well, as shown in HCl, H2SO4 and H3PO4, which have 1, 2 and 3 ionizable hydrogen respectively. Then I also told you that why this definition cannot be made to apply to bases, because and why we don't say that a salt is a chemical compound formed by replacing the carboxylic group, the hydroxyl ion of a base. And I told you the reason that firstly, a base by definition is something that neutralizes an acid, and for that you don't necessarily need a compound with an OH group in it. Instead, carbonates and oxides can also be used. Therefore, this definition becomes incomplete. Why? Because it will not encompass all the bases. Secondly, I also told you that there are some bases like ammonia in which absolutely no replacement takes place when the neutralization is taking place. For example, NH3 plus HCl, it's kind of an addition reaction. I'm not going into the detailed mechanics of this reaction that you're going to study in A levels, how this NH3 becomes NH4 plus, and how this HCl becomes only Cl minus, and then this reaction takes place. The mechanics of this reaction will be covered in A levels. Anyway, the point is that it's not necessary that uh, any kind of replacement takes place in the base for the formation of a salt. Then I told you that salts can be soluble or insoluble, and therefore and this thing, the solubility or insolubility of a salt, is going to impact on the method that we will be employing to make that salt. And for that purpose, we needed to know what salts actually dissolve in water and what salts do not dissolve in water. For that, I gave you people a solubility table, and here we go about this table. I told you that all group 1 salts, regardless of the anion, are soluble. Why did I say anion? Because group 1 produces cations only. So the other ion that we need for making the salt will be an anion. Then I told you that all ammonium salts, regardless of the anion again, are soluble. Then I told you that all nitrates are soluble regardless of the cation. And then I showed you that in this table we have put ammonium and nitrates together. The reason being so that both the nitrogen containing ions are kept together, and that will help you in memorizing this table. Then I told you that all ethanoates are soluble regardless of the cation. Why? Because ethanoate ion is an anion. Then I told you that all halides are fluorides, chlorides, bromides, iodides and astatides. They are soluble except the halides of lead, mercury and silver. That is LMS, like my status. Sulfates. All sulfates again are soluble except like my status center back, lead, mercury, silver, calcium and barium. Finally, I told you that all carbonates are insoluble except those of group 1 and ammonium. Okay, I just noticed a mistake that I made yesterday, and the fact is that ammonium is a cation, not an anion. So please correct that in your notes if you were making notes with my video. So correct that with you, please. Now, coming to the formation of salts. I told you that insoluble salts can be prepared by precipitation, and inshallah we'll cover that in this video. Then we talked about soluble salts, and in order to make soluble salts, there can be two basic methods. The first method involves both liquid reactants, and that's called titration, and we'll be coming to that shortly. And uh, the second method is using one liquid reactant, which is going to be an acid, and the other solid. And for solid, we have three options. We can either have a metal, which that is only moderately reactive metals will be used. That means we won't be using some super reactive metals like potassium, sodium, aluminium, etc. Uh, and we won't be using metals which are too less reactive, for example, copper, mercury, etc. So I made the reactivity series here, and I mentioned that these are the moderately reactive metals. Remember, we had hydrogen in this reactivity series as well, which was there for comparison. That means that the elements above hydrogen in the reactivity series are more reactive than hydrogen, and therefore they can displace the hydrogen ion from the acid and take its place. And that explains why the two unreactive metals cannot be used to make the salt directly from the acid, because these metals do not have the power to displace hydrogen from their acid. I just noticed another mistake. I was writing it from the mnemonic, so I mistakenly wrote good in place of gold. So here we go. Okay. Then we talked about oxides and carbonates, and these are the solids that will be used when the metal is too unreactive or when it is too reactive as well. But again, I told you that when we have a metal that's too reactive, for example, group 1 metals, we'll be using titration. The reason being that the oxides and carbonates of group 1 metals are deliquescent. That means they absorb the water vapor from the air to form liquids. Yes, and then obviously we'll be having both liquid reactants, and finally we'll be obviously going on with titration there. So the general steps were to add excess solid to the acid, and we'll be stirring continuously until no more of the solid dissolves. Finally, we'll filter the mixture. The residue will be the excess solid, and the filtrate will be our salt solution. We will crystallize the solution, and we'll obtain our salt. So before we get on to titration, why? Because crystallization is a process that will be coming out in titration as well. So we'll first discuss what exactly crystallization is. So I'll move here, and let's get to crystallization. Crystallization. So if you're asked to define crystallization, it is a process of obtaining salt crystals. This crystals is important. I'll explain why this is important here. From its solution. So how is crystallization different from evaporation to dryness? I'll tell you that. Uh, I'm sorry I mentioned it a bit prematurely. Anyway, so the first step in crystallization will be that we'll take the filtrate. Here's a filtrate. This I'm sorry for the inconvenience. This is the filtrate. We'll take this filtrate, and what we'll do is that we'll first heat it under a Bunsen flame, right? Uh, Heat the filtrate Yeah, we'll be more general and we'll say heat the salt solution under a Bunsen flame, under a flame, or you can also use a hot plate, whatever, until saturation. What does this mean? Remember, firstly, that a saturated solution is a solution in which no further solute dissolves. Saturation, a saturated solution is the one in which no further solute dissolves. So now, what will happen is that when we'll start heating the solution under a flame or a hot plate, obviously the liquid is going to start evaporating from this. And we'll be having less and less amount of solvent left in this solution until a time will come when we have a lot of solute but we don't have enough solvent. So there will be a point in between, like let's draw a graph to understand this. I'll remove this graph later on. Let's say that at the start of heating, that is time is equal to 0, we had this much solvent. Then as the uh, heating proceeded, we had a decrease in the amount of solvent present. However, if we take a look at the amount of solute, this is going to be a constant, obviously, because the solute is not evaporating at all. I'll try to draw a straighter line. Yes, the solute remains constant throughout all this time. So what will happen is that there will come a time in the heating process when the amount of solvent present in the mixture is such that if we stop the heating at that point and we try to dissolve any more of the solute, it will not dissolve. That, let's say this is this point. Alright, I'll use a different color, these are too similar. Let's say here is that point, this point. If I add any more solute to the solvent after this point, remember that we still have this amount of solute in this. If we add any more solute, we won't be getting any kind of dissolution. So this is the point of saturation. How will we know that the saturation point is reached? So now I'm telling you the method for that. You need to know that method. Saturation is checked by putting a glass rod into the solution time and again. Right. So a time will come when as soon as you put the glass rod in the solution, let's say that we are heating the solution here, and you put the glass rod and you take the glass rod out. When you take the glass rod out, you will see that immediately crystals of a salt are forming. Some crystals are forming. That is the saturation point. So coming again, saturation is checked by putting a glass rod into the solution time and again. The point when crystals of a salt, okay, when crystals of a salt form on the glass rod is the saturation point. Now this is particularly important from the from your paper 4 point of view. You can be asked about how to test for saturation in your ATP papers. So once we have heated the solution to saturation, we will turn off the flame. Turn off the flame and let the solution, let the solvent, I would rather, it will be more accurate, and let the solvent evaporate on its own. Leaving the crystals. Right. So after the saturation point is reached, I'll turn off the Bunsen flame and I'll let the remaining saturated salt solution evaporate on its own. Now, and this is going to give me the salt crystals. So now you should be asking me that why don't we continue with the heating? The reason is that a crystal is formed uh, because of the presence of some water molecules. Let's talk about copper sulfate. Copper sulfate is CuSO4. For copper sulfate to be present in its crystalline form, there must be some water molecules present in the copper sulfate. Therefore, the blue copper sulfate crystals that you see, it's not just CuSO4, instead it has some amount of water present in them. To be exact, there are 5 water molecules for one copper sulfate molecule, which maintains the crystalline structure of copper sulfate. So this is a very important point. Now what will happen is that if you heat these copper sulfate crystals, the CuSO4 and with 5H2O, you will get a white solution, a white powder. This white powder will be only CuSO4. Remember, a powder is not crystals. So these CuSO4 crystals, because of the loss of water as a result of excess heating, becomes a white powder of copper sulfate with no H2O molecules. So if we continue heating, what will happen? And this water is called the water of crystallization. Why? Because it is the presence of this water that maintains the crystalline appearance of a particular crystal. So if we continue heating beyond under a Bunsen flame beyond the saturation point, what will happen is that this remaining uh, that this water of crystallization will also evaporate, and we won't be getting crystals of a salt. Instead, we would be getting a powder of that salt. So this is what crystallization actually is. I hope this is clear. If you have any problems, if you still have any problems, drop down your queries in the comments and I'll try to answer those questions privately to you people. Right. So now we are done with the thing which was left in this video, and that was crystallization. Coming to titration. Titration is an acid-base reaction. What we do is that we add uh, an acid to a base or a base to an acid, uh, and finally we see the endpoint. So what we do here is, I'll draw a diagram first. So firstly we have a conical flask, in which we have a base. I'm taking a base, and I'll tell you why I've taken a base in a conical flask. And how will I add this base here? I'll pipette it out. I'll use a pipette. I'll use a pipette filler. It's a structure like this. I'll use a pipette filler and fill the pipette with the base up till the mark. There's a mark on the pipettes. I'll fill it till this point, and then I'll release the base into the conical flask. There we go. Then what I'll do is I'll take the acid in a burette Okay, this is the burette. The burette has a tap in it. Huh? And I'll gradually add drops of acid into the conical flask. And remember that I'll be adding another thing to the conical flask before I start adding the acid. And that thing is an indicator, which is going to tell us the point at which the neutralization is complete. So now, firstly, this titration is a method of choice for forming salts of group 1 metals. This is the method of choice for forming group 1 salts. When I say method of choice, it means that it is the preferred method. The reason why we are using this method to form group 1 salts is because group 1 metals are extremely reactive and their oxides and carbonates are deliquescent. That means they turn to liquids themselves. So obviously we then have both liquid reactants, and that's how we'll go about the reaction. So the first step is, number 1, pipette out the base, or you can take an acid as well, into a conical flask. Full stop. Add a small amount of a suitable indicator. I'll discuss some suitable indicators shortly, inshallah. Right. Step 2. Fill the burette with the acid or the base. Now remember, see, I have reversed the order here. I had base here first, I have acid here. That means if you had taken the base in the conical flask, so obviously you will be taking the acid in the burette, and if you had taken acid in the conical flask, obviously you would be taking the base in your burette. Fill the burette with the acid or the base. Number 3, slowly add the acid or the base from the burette to the conical flask. Until there is a change in color. And this is the reason why the indicator was added, to tell us that the reaction is complete. So if there's a change in the color, the reaction is complete. Now this is called the end point. This is called the end point. Now see, we have the salt solution here. Obviously we have the base, we added the acid, neutralization took place, and we got the salt solution. But this salt solution is not pure. The reason being that we had the indicator in it, and this indicator is acting as an impurity for our salt solution. So what we'll do is, we are going to do the titration again. What we'll do is, we'll record the volume of the acid or the base, or the base required for neutralization, full stop. Number 5, throw away the first titer. Obviously, because it's polluted, we don't need it anymore. So the solution that forms here, we'll throw it away. And what we'll do now is we will uh, repeat step 1 minus the addition of a indicator. So here we go. Number 6, repeat step 1 minus addition of indicator. Number 7, add the volume of acid or base recorded in step 4 to the conical flask. So now we have our pure salt solution, or roughly pure. Number 8, the last step. We now get our salt solution. Crystallize. Now after we have crystallized, we'll be doing another procedure. What happens is that whenever we are doing the titrations, we always inevitably get a slightly greater amount of the substance that we are adding in the burette. We are adding from the burette. So I had a base in this in the conical flask, and I had an acid in the burette. So what will happen is that as I add, inevitably a slightly greater amount of the acid will be added to the conical flask than is needed for the neutralization to take place. That means there is a small amount of impurity still present in our salt solution. So in order to get rid of that, after we have done the crystallization, we are going to wash the crystals. And how will we wash the crystals? Obviously, we won't be putting them under a running tap. Instead, we'll be spraying distilled water onto the crystals, and we'll finally dry the crystals down. So we have our 9th step. Wash the crystals by spraying distilled water on them. And number 10, dry the crystals by dabbing them between folds of filter paper. So this is the procedure for forming salts, soluble salts. Now coming to suitable indicators. Common indicators are litmus, phenolphthalein, this is a very difficult spelling, so excuse me if I have gotten this wrong. I think I haven't gotten this wrong, but if I have, please excuse me for that. And we have methyl orange. These are the most common indicators that are used. So you should remember the color changes for these indicators. So remember, we'll first put acid, then neutrality, and then base. Acid, neutral, and base. So remember, in acids, Most of the indicators are red except phenolphthalein, remember. So in acid, litmus is going to be red. In methyl orange, litmus again is going to be red. But when we come to phenolphthalein, it is going to be colorless in acid. Right. Now coming to neutrality. Alright, we'll do the basic part first. Litmus under the influence of a base is blue. Okay. Phenolphthalein under the influence of a base is pink. And methyl orange under the influence of a base becomes orange. Yeah. I don't have an orange pen with me, so I'm sorry, I'll have to suffice with this multicolored thing. Now coming to neutrality. When in a neutral solution, for example water, litmus will be purple. Phenolphthalein is going to be colorless again. And it might obtain a slightly pinkish tinge as well. Methyl orange finally. Here's red, here's orange. Methyl orange becomes yellow in a neutral solution. So these are the color changes that you need to remember. So in this case, what should be the suitable indicator? Remember, using phenolphthalein here wouldn't be the wisest of options because we have a base here, and already you can use phenolphthalein here as well, and when phenolphthalein becomes colorless you can stop, but the preferred indicator in this scenario would be methyl orange, which would be orange here, and then finally alright, we'll prefer to use phenolphthalein. Okay, so these are some of the common indicators here. Now I'll tell you why I chose to take a base in the conical flask and an acid in the burette. The reason is that you have studied in the chapter of acids and bases, you might have studied in the chapter of acids and bases that bases are slippery and sticky. So what happens is that if I take the base in the burette, it will tend to stick. And you see there's a tap here, and there's a slightly intricate mechanism here, and the base can remain stuck in this part of the burette, which is very difficult to rinse out as well again. So for this purpose, we prefer to use acids in burettes because they are easy to rinse after use, and easy to remove the traces of acid after use. So that's why I took an acid in the burette, and I took the base in the conical flask. There are some other complications as well, some experimental precautions and accuracy measures, which unfortunately, because of shortage of time, I won't be able to do in this video. I'll be doing a later video on that, inshallah. Uh, Now coming to the last thing in this chapter, and that is preparation of insoluble salts, and that is precipitation. So, where to continue this? Alright, I'll just do it underneath. So coming to precipitation. So like titration, precipitation again is a procedure which involves both liquid reactants. Involves both liquid reactants. And what we do is we'll mix both the liquid reactants together. Simply. Now, what kind of a reactant will we use? What kind of liquids will we take? Let's say that I want to form barium sulfate. If you remember the solubility table, we knew that sulfates of barium are insoluble. So if I want to form barium sulfate, I obviously need a source of barium ions. We need a source of barium ions, and we need a source of sulfate ions. So this is what we need: barium ions and sulfate ions. So the liquids that I'll take, one liquid will be a solution which contains barium ions, and the other liquid will be a solution which contains sulfate ions naturally. So one of the liquids will be the source of the cation, while the other will provide the anion. So again, if you recall the solubility table, you will know that all nitrates are soluble. Therefore, a suitable solution to become a source for the cation would be a solution of barium nitrate, BaNO3 2. I'm writing AQ here to indicate that we have an aqueous solution. And a source of sulfate ions can be, maybe you can use the sulfuric acid, or you can use sodium sulfate as well, solution of sodium sulfate, Na2SO4 aqueous obviously, or any other source of sodium sulfate. Now what we'll do, any other source of sulfate ions, which is a liquid. Now what we'll do is, we'll mix both of these together. And as soon as we mix them, let's say that I had barium nitrate in this, and I added sulfuric acid to this. As soon as I add sulfuric acid to barium nitrate here, barium sulfate will start forming. This is barium sulfate that I have tried to draw. So this is barium sulfate. This is barium sulfate. What we'll do is that so it's basically kind of an exchange reaction. What happened is that barium combined with the sulfate, and the nitrate remaining from barium nitrate will combine with H2, and obviously what will be remaining in the solution would be HNO3, two molecules of HNO3, that is nitric acid. So this is basically, as we just saw, kind of an exchange reaction. These reactions are actually called double displacement reactions, but we'll leave that for now. Right. So what we'll do is that obviously we have the solid formed, which is our precipitate, and we have nitric acid around it. We will filter out the solution. We'll filter out this mixture. The residue will this time, see, in the previous case when we were forming soluble salts here, the residue was not needed and the filtrate was needed. Here it is the opposite. The residue is what we need and the filtrate is the byproduct. So after we filter out, uh, finally after addition of the, we'll continue here. Number 1. Number 2. Mix both liquids. Number 3. Filter the mixture. Number 4. The residue this time is our salt. What we'll do is we will wash the salt crystals and we'll dry them. Wash and dry the salt crystals. So now this brings us to another point, the last point of this chapter, that why don't we add solid barium to sulfuric acid to form the precipitation, to form the precipitate? The reason is something called the blocking action. What is the blocking action? See, I have sulfuric acid here and I add a lump of barium metal. So yes, the reaction will start, but what will happen is that barium sulfate will form on the surface of the block of barium metal. And this barium sulfate, which has formed on the interface, on the acid barium interface, is going to stop the remaining barium metal from reacting with the sulfuric acid. This is called the blocking action, and this is the reason why we won't use the solid barium metal to form barium sulfate. With that, we are done with the formation of salts. If you have any queries, leave your queries in the comments and I'll try to answer them. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.